Okay, so students often wonder where these notations like dy by dt or dx by dt come from, and it's a really good question. They actually come from the Leibnitz notation, and Leibniz notation comes from the man Leibniz, who was one of the co-founders of calculus. Leibniz and Newton actually developed calculus independently. The story goes that Newton developed it as a way to explain his physical phenomenon, while Leibniz, a mathematician, developed it around his understanding of math, but they were based in the same principles. As it goes, Leibniz, who was in cahoots with the Bernoulli family, they really liked Leibniz, he actually reached out to Newton to work together to collaborate to develop calculus, but Newton, having ties with the Royal British family, didn't want to participate, and so as it turned out, once they both developed it, Leibniz was essentially sued and went to the Royal Order Court, and it was found that Newton was the true father of calculus, but truly, the real story is that they developed them separately. Now, this is relevant because Newton developed calculus for physics, and Leibniz developed calculus for math. So, understandably, Newton's notation is representative of physics, whereas Leibniz notation is representative of what the derivative is, and that is that it is a slope. That is derivative. So in calc, we have instantaneous rate of change. I like to call it IROC, and average rate of change. Okay, and IROC is slope, as is AROC. AROC is, y2 minus y1 over x2 minus x1, and that's our m, right? That's our AROC. It's an average rate of change. You're just looking for the slope. IROC is slope as well. We call it usually in function notation f of x2 minus f of x1 over x2 minus x1. But the difference between AROC and IROC, and in case this bothers you, I can easily change it so it's also in function notation, just so you can see that they're the same. Okay, the difference is that this AROC over here kind of is the whole point of it is that x2 and x1 have some amount of space. That's the average part, and you're looking for how something changes over space. So when you're talking about, the x and y axes, you're actually looking at a difference between x2 and x1, and there's some level of space between them, right? We have this area between them that we're actually kind of concerned with, and we're talking about the average rate of change, or kind of the total rate of change is almost a better way to describe it, over that space. But x2 and x1 have space. Instantaneous rate of change, we're no longer worried about space between x2 and x1 because we want to know what's happening at an instant, at a specific x. So the way we kind of originally calculate these in a typical calculus class, I'm not totally sure if this is how you guys did it, but in a typical calculus class, how one might calculate it is they are looking for, say, call this x, and we're looking for an instantaneous rate of change at some x. So what we'll do is we'll pick something to the left of it, we'll call that x1, and something to the right of it, and that x2. And these two are converging on that x. And this x is really what we're interested in finding the instantaneous rate of change of. We want to know what that point is. But we use these two surrounding points, x2 and x1, to kind of bring them together. So we pick an area of space that is really, 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 really small. Infinitely small, in fact, okay? Infinitesimally small, so there's practically no difference. So that x2 minus x1 is approximately approaching 0, right? That's what we want to do. We want to get it so x2 and x1, the difference between them is 0. So they're basically converging on that x spot. So x2, x1, and x are all the same thing. They're all at the same place. And that infinitesimally small difference is what we're using, quote unquote, for IROC. So that's where this notation of the limit as x2 approaches x1 comes from. We're looking for the slope as the 2 points are converging together. That is the instantaneous rate of change, and as you probably recognize, this is the very definition of a derivative. Okay, so that understanding of what the notation means, or what the definition of IROC is key. And this is what Leibniz leaned into when he used his notation, is this relationship of the derivative with what it is, which is slope. It is slope at an instant instead of slope over some level of space. Okay, so if you buy that, then you will kind of get into where Leibniz notation works on. And Leibniz notation is this idea of dy by dx. And it really is based in this idea that when we find f prime of x as the limit, and I'm actually going to use a different notation here, which is equivalent to this notation here. It's just what I prefer, which is delta x, or h approaches 0, f of x plus h minus f of x over h. So it leans into this, understanding that h can also be written as delta x, right? It's the difference. So f prime of x equals the limit as f of x plus delta x minus f of x all over this delta x. And if we wanted to think about this a little bit as delta x approaches 0, as we wanted to think about this a little farther, what we're really talking about here is the change in f, right? And that's really just the change in y, because we often use y and f interchangeably when we're talking about functions. So we could think about this even more simply as the limit as delta x processes to, or goes to 0. We're talking about what the change in y is over the change in x. And this little triangle is actually delta, the Greek. So we use delta as change in science all the time, and that's what's using here. But I do want to point out that delta starts with d. Right? So this Leibniz notation is literally representing this function where delta is the instantaneous change of y over the instantaneous change of x. So when we're talking about derivatives, are the instantaneous change of y over the instantaneous change in x, right? So this limit as delta x approaches 0 of change of y over change in x can be written as delta f, or delta y, excuse me, over delta x, and that's where the notation comes from. And this is counter to Newton, who just did this. It means the same thing. It's just Newton was way more interested in the physics application, so he didn't really see a purpose for keeping track of this slope. But Leibniz, a true mathematician, saw the beauty of the connections between what we know in algebra about slope and what we know about derivatives, and that's where the notation came from. And I do have to mention, this is actually not true Newtonian notation. Newtonian notation looks more like this, and we've used this, we've adopted this, and this you'll see in every so often, you'll see in, especially in physics books, but I just want to mention that it's not true Newtonian. And so if you hear at some point that it is, it's not, but we can certainly attribute Newton to this notation. Okay. Attribute this notation to Newton, I should say. Okay, so there can be some helpful ways to consider this function. We call dy by dx is a derivative. This is the same as y prime, right? So we know that, but what we're not really realizing is that this is actually an operator as well. And so it gives us information about what y is with respect to, what y was changing with respect to. But it also acts, this part in pink also acts as an operator. And so it tells us what we're finding the change with respect to. So we can apply this to any function, whether it's a function in y, or if it's a function in f, or it's a function in g, or whatever, and it's telling me to find the derivative with respect to x. So I tell you this because let's say I have y equals x squared plus 2x plus 5, okay? If I apply the operator, which is d by dx, to both sides, like we would in an equation, we actually get that this is dy by dx, because the derivative of y is 1, and we have that dy by dx kind of like implicit, right? And then we have 2x plus 2. And one thing I like to tell my students is that technically this is dx by dx, because we just found the change of x with respect to x. But dx by dx is just 1, which is why we drop it. So one of my kind of frustrations with the implicit is that, we teach students to do this y prime or dy by dx where appropriate, but we don't necessarily tell them that this is technically dx by dx. It's just that dx by dx is 1, so we don't write it, because it's how x is changing with respect to x. And because x is the same thing, it changes at the same rate as itself. So that change is with respect to itself is just 1, okay? But, and I wrote dy, my bad. Change that. So that's why we do, with implicit, we do y by dx, but we don't include the dx by dx. And because on the left side, we're talking about how y is changing with x, and on the right side, we're talking about how x is changing with x. And so we need that reference point on this left side, but we don't need it on the right side because it's kind of silly to talk about how x is changing with x. So when we have something like, oh, I love the a squared plus b squared equals c squared problems, where we're doing like something with a right triangle. Like we've got some problem where, and I see these all over the place. This is a very common setup of problem where we got a right triangle where we have a changing and b changing and c is constant or something like that. So if I were to take this function, which has no x's, and apply an operator, usually, like you said in your email, d by dt, what I'm asking is how this function, this side of the function, and how this side of the function is changing with respect to time. And so I might say that it is 2a dA by dt plus 2b dB by dt equals 2c dC by dt. And I have to put all those because in each of these cases, these are all variables that I might be looking for, but they're all changing with respect to time. And so that's where that difference between d by dt, dy by dt, and dx by dt, because if you're looking to see how y is changing by time, that will change differently from how x is changing with time. And that's really the thing that comes into those related rate problems. But the thing that you just remember is that no matter what you're dealing with, when you see this, you're literally thinking about how y is changing with time, or with x, excuse me. And down here, you're seeing how each of these are changing with time. And that anytime you have anything, like even if you have a 6, right? If you apply an operator to it, I should say 6, and I should apply the operator, which is d by dx. You're finding the derivative of 6 with respect to x, which is going to be 0, right? Or if you find y d by dx, that becomes dy by dx, because you're finding how y is changing with x. Or if you have 6x d by dx, since this is an x term, now you're saying that it's changing as a 6. So that d by dx acts as an operator, is telling you what you're finding the derivative of with respect to. And then that becomes the piece that you need, okay? So if you had 6x by d by dt, okay, now that becomes 6 times dx by dt because I'm wanting to reference that I'm saying how x changes with respect to t. And that's all Leibniz, because we're applying the operator, we're finding the derivative formulas with respect to something different than what you may have expected in the denominator.